So we're going to investigate binomial probability and sigma notation, and these are two different topics, but that go really nicely together. So let's start off by thinking about the probability of flipping two coins and getting two heads. So if we think about like the events heads and not heads, where not heads is just simply getting tails. Well, we can make a little probability tree. And on each flip I either get heads or not heads, or heads and tails. And for this particular problem, the probabilities are the same for everything. So I'm just drawing this all out, and we're going to learn a method that is much cleaner than having to make these trees. But for now, let's think about, each probability is 1/2. So I'm just filling in my tree with the probabilities on the branches. And if we're thinking about, like, for me to get two heads, there are 3 different pathways that get me there. So one pathway is here, getting sorry, one second. So getting heads, heads and not heads, getting heads, not heads and heads, and getting not heads, heads, heads. In all these ways, I'm getting 2 heads. And what we notice is that for each of these pathways, there are 3 different pathways, and for each one, the probabilities are the same. It's just 1/2 times 1/2 times 1/2. And this 3 represents the number of ways that we can get there. So number of pathways. And for this, 2 of the 1/2 means that's me getting 2 heads. And then this other 1/2 is me getting not a head. Okay, well, let's look at another example of that. So let's imagine that instead we're rolling 3 die, or 3 dice. And I want to get 2 6s. Well, let's call event S getting a 6. So you could either get a 6 or not get a 6. Get a 6 or not get a 6. So we could fill out this chart. And as we're filling this out, let's start thinking about what patterns are we recognizing so that we don't always need to be filling out this chart. Well, let's fill out some probabilities. The probability of getting a 6 is 1/6, and not getting a 6 is 5/6. So we have all of these probabilities here. So I've filled out the probabilities and shaded in the pathways that will give me exactly 2 6s. And so what you'll notice is in each pathway we're going to have a probability of 1/6 times 1/6 times 5/6. Because I'm going to have 2 successes, which is a probability of 1/6, and 1 failure, which is a probability of 5/6. And since there are 1, 2, 3 pathways, we're going to have 3 pathways times 1/6 squared times 5/6 to the 1 will be my probability of 2 6s. So where are these numbers coming from? Well, let's make a leap here. the 3, the 1/6 squared, and the 5/6. And I'm going to put 5/6 to the 1th. So this 1/6, that's the probability of a success. And this 5/6, well, that's just 1 minus the probability of a success, which equals the probability of a failure. Okay, and this 2 up here, well, that was the number of successes. And this 1 is simply the number of failures. But what about this 3? What is that coming from? Well, that 3 is the number of pathways that will lead me from 3 choices to get 2 things. I had 3 places where I could get 2 successes. So this is simply 3 choose 2. That's where that number comes from. Where the 2 is the number of successes. So this is a really important idea, and this is called the binomial probability distribution. It's called the binomial probability distribution because 2 things can happen. I can either have a success or I can have a failure. So, as I said, binomial probability looks at something that can either will or will not happen. So the event and its complementary. Let's look at a couple examples of this. So let's just assume that there's a 9/10 chance of being extraordinarily happy when you arrive at Nueva. In 10 days, what's the probability of being happy exactly 3 times? Well, you could go about creating a tree where you're like happy, not happy, happy, not happy, happy, not happy. And this tree is going to branch, each one of this would be like our first event and our second event, and this would branch out 10 times. But if we use that idea that we were just thinking about, why don't you pause the video right now and see if you can write out the probability using the idea from the last 2 slides. Okay, well, there are 10 days for me to choose 3 times of being happy. So there are 10 days where I'm choosing 3 days to be happy. And on these 3 days when I'm happy, the probability of being happy is 9/10. And how many times do I have to be happy? Well, 3 times. So it's going to be 9/10 times 9/10 times 9/10. And on the other 7 days, I'm not going to be extraordinarily happy. So that's going to be 1/10 to the, how many times am I not extraordinarily happy? Well, 7. So this, and it's unsimplified, but this is the probability of being happy exactly 3 times. And what it's saying is that there are 10 events where I'm having 3 successes, so this events plus successes is the number of ways or the number of pathways on the tree. And then I'm going to multiply that number of pathways by the probability of each pathway. And they're all going to be the same because I'm going to have 3 times being happy and 7 times being not. Now, hopefully it's 10 times being happy. Okay, what about this? What's the probability of being happy at least 2 times? Well, these at least questions are really interesting to look at. If I'm happy at least 2 times, let's think of this as being a pie chart that's 100%. So if I'm happy 0 times 1 time, well, that's not being happy at least 2 times. And then we have 2, happy being 3 times, happy 4 times, 5, 6, 7, 8, 9, 10. So everything in this, let's see, everything in this pie chart here would satisfy me being happy at least 2 times. And everything in this part doesn't satisfy it. Well, what's easier to find? It's much easier to find, it's much easier to find this section in here, because there are only 2 events, being happy 0 times or being happy 1 time. So if I say, like, what's the probability of being happy 0 or 1 time, that's just 1 minus the probability of being happy at least twice. Or probably the better way of writing this is the probability of being happy at least twice is 1 minus the probability of being happy 0 times or 1 time. Okay, so let's use this idea. Well, so 1 minus the probability of being happy 0 times. Well, there are 10 times, and I'm choosing 0 times to be happy. And the probability of being happy is 9/10, and I'm happy 0 times. And then the probability of me being sad is 1/10, and I'm sad 10 times. And then we also want to add up the probability of being happy only once. So plus 10 times, and I'm choosing 1 time to be happy, and then 9/10 to the 1 times 1/10 to the 9. So this entire sequence, or is the probability that I'm happy at least 2 times. And so what I did is I found the probability of being happy 0 or 1 time, and I subtracted 1 from that. And when I subtracted 1 from it, I get the region that I'm looking for. Okay, well, I want to introduce the idea of sigma notation because it's really helpful for these types of problems. And many of you guys have used sigma notation before, but for some of you it will be new. So the idea of sigma notation is it's a lot like pi. So it adds terms. Unlike the pi operation that multiplies terms, so remember if we had like pi I equals 0 to I equals 3, and then let's just say we had like 4 minus I, this would be 4, and then I would become 1, and then times 4 minus 1 times 4 minus 2 times 4 minus 3. You guys have been working with pi operation a bunch. Sigma notation works exactly like that, except instead of being multiplying, it's adding them. So if we had like I equals 0 to I equals 3 and 4 minus I, this would equal, well, 4 plus 4 minus 1 plus 4 minus 2 plus 4 minus 3, which, just to simplify, be 4 plus 3 plus 2 plus 1, which equals 10. Well, okay, let's use this idea of sigma notation with binomial probability because it's incredibly helpful. So let's think about this. Same problem we just did. 9/10 chance of being extraordinarily happy when you arrive at Nueva. In 10 days, what is the probability of being happy at least 2 times? Well, in the last problem, instead of having a longer strand, let's think about this idea of finding that being happy 0 or 1 time. And let's just write out what I had before. So it was 1 minus 10 choose 0 times 9, let's erase that, 1 minus 10 choose 0 times 1 times 1 times 10 choose 0 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 times 1 times 10 choose So as I'm filling this out, try to think about how you might use sigma notation. So 9/10 to the 0 times 1/10 to the 10 plus, okay, sigma notation, plus, and now it's going to be a very similar thing. 10, choose 1 instead of 0, times 9/10 to the 1 instead of 0 again, plus 1/10 to the 9th. Oh, okay. So what are the things that are changing? This is changing. That's what I want. How many successes is changing, and that's changing, and this is changing. So how could we rewrite that using sigma notation, which will be much cleaner? Well, this would just be 1 minus the sum. Well, let's go from I equals 0, and I want two terms, right? I've got this term and this term, so we're gonna go to I equals 1. And how is this going to work? Well, we're going to have 10 choose I times 9/10 to the I plus 1/10 to the 10 minus I. Oh, that's a really cool way of writing it. Okay, let's look at one more example of this. Okay, so let's say, just to keep it totally like a generic problem, the probability of H is, I don't know, 0.7. So therefore the probability that H doesn't happen is 0.3. And we're going to have 25 events. So it's going to happen 25 times. What's the probability that H happens at least 5 times? Well, there's a couple ways of writing this, but using sigma notation, I can just write this in one sigma notation. So if we think about what's going on, we've got 25 events, and we're going to choose some number of successes. And then, however many, and this says successes there. So then however many successes we have, we're going to have the probability of a success is 0.7 raised to the number of successes. And then the number of failures we have, well, the number of successes plus failures must add up to 25. So this is going to be 25 minus however many successes I have. Alright, well I want to find the probability of having at least, of H happening at least 5 times, which means that it could happen 5 times, 6 times, 7 times, all the way up to 25 times. So the probability of that happening is going to be the sum of the probability of it happening 5 times, plus the probability of it happening 6 times. So it's going to be a bunch of sums. So what we're going to be adding up is the sum from I equals, well, until I have my first success. So from I equals 5 all the way up until 25 successes. So all the way up till I equals 25. And then we have 25 things to choose from, and we're choosing I successes. And if we have I successes, then we have 0.7 probability for success raised to the I, because we're having I successes, and then 0.3 times 25 minus I. And this is the probability of at least 5 successes.